Assalamualaikum dan selamat sejahtera. My name is Muhammad ISMAIL and I'm from class 2 BMH.
Assalamualaikum. My name is AZIMAH binti AZMAN with matrix number B0920100216. I am from class of 2 BMH S101.
Assalamualaikum warahmatullahi wabarakatuh. Nama saya Muhammad AIMIZARITH bin Marizal dari kelas 2 BMH section 111.
Assalamualaikum warahmatullahi wabarakatuh. My name is FATINI bin RAZAK. My matrix number is B09201007.
So, objective for this lab linear conduction is to show how heat conducts linearly along a solid bar and around a solid disk of uniform dimension and material. Second is to show how different materials in contact can effect linear heat transfer. Thirdly is to show how you can calculate the experimental thermal conductivity of the material in a solid bar. And lastly is to show how thermal paste helps to give a good thermal conduction. And then introduction for this lab is conduction is the process by which heat is directly transmitted through the material of a substance when there is a difference of temperature between adjoining regions without movement of the material. The linear heat conduction apparatus is designed for students to study the principles of conduction heat transfer. The student is able to determine the relationship between the rate of heat transfer and temperature gradient, the cross-sectional area, and length of the conducting path. This experiment unit shows how heat conducts linearly outwards from a central heat source through a metal disc of uniform dimension. The equipment that needed for this lab linear conduction is the VDAS hardware and software. And secondly is the linear heat conduction experiment.
First, measure the ambient temperature before starting the experiment. Next, put the linear heat conduction experiment, start with brass middle section, onto the base unit. Third, connect the water supply pipes. Next, switch on the water supply to allow the water pass through the experiment. Connect the thermocouples. Switch on the base unit and the heater. Set the heater to 30 watt and wait the temperature to stabilize. Record temperature 1 until temperature 7 in table 1. Repeat the test with 50 watt and 90 watt. Repeat the procedure 1 until 7 with stainless steel middle section and copper middle section. Switch off the heater and water supply after use.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad AIMIZARITH bin Marizal and my matrix number is B0920100090. and today I will continue this presentation with our result. So for table 1, as you can see, the power is 30, 50, 60, 70 and 90. So this is all the result for T1, T2, T3, T4, T5, T6 and T7. So the distance from T1 we got 0, 0.02, 0.04, 0.06, 0.08, 0.1, 0.12. Next to table 2, same as table 1, this is the result, and the power is 30, 50, 60, 70 and 90 also. The distance also same. For table 3 also same as table 1 and table 2. Then the data analysis for this experiment. As you can see, this is the graph of temperature versus distance for brass material. For stainless steel, and then for stainless copper.
Assalamualaikum. My name is AZIMAH binti AZMAN with matrix number B09202216. So for the discussion number 1, calculate the gradient of the charge. What does this gradient represent in the conduction equation? So this is the formula of gradient, which is M equal to delta temperature divided by length. This is the gradient charge that we have calculated for brass, stainless steel and stainless copper with different power. So a temperature gradient is a typical quantity, is a physical quantity that describes in which direction and at what rate the temperature changes the most rapidly around a particular location. The temperature gradient is defined as the change in temperature per unit length. Temperature gradient is the change of the temperature with distance. A positive gradient is a temperature increase with an increase in distance, and a negative gradient is a temperature decrease with an increase in distance. Then, conductive heat transfer is a transfer of heat down a temperature gradient between the two bodies in close physical contact. The rate of conductive heat transfer depends on temperature gradient between the two bodies, the area contact, and the conductive properties of these bodies. Next, for the discussion number 2, use the two furthest reading T1 and T7, the given distance between them, the heater power and the bar area with equation 5 to calculate the thermal conductivity of the metal bar. Compare it with the typical value given in table 1. Explain the cause of any error of the different value of the theoretical and experimental thermal conductivity. For the brass, firstly, we need to find the A, which is area. Then by using the equation 5, we can get the value of K. Then for the experimental value is equal to 93.1.5 and theoretical equal to 96. Then for stainless steel, by using the same equation, we can get the experimental value equal to 113.921 and theoretical equal to 15. And last one, stainless copper. By using the same equation also, we can get the experimental value, which is equal 85.51 and theoretical equal to 123. Then the cause of error for the different value of the theoretical and experimental thermal conductivity is distance for the heat to travel from heater to material. The heat might not optimally transfer. Then human error when taking the temperature. Thermal resistance of the test material can be affected by surrounding temperature. And last one, the effective thermal conductivity change as a result of material aging. Then for discussion number 3 is what can you observe from the gradient of the chart for each heater power setting? The slope of the temperature curve on a T L diagram is referred to as the temperature gradient. When temperature decreases with increasing distance, heat is transported in the direction of decreasing temperature, and the temperature gradient becomes negative. When we look at the gradient for each heater power level for all the materials, we see that all the gradient values turn negative as the distance between the heater increase. When the temperature rises and the distance falls, the gradient becomes positive.
So we move to discussion number 4, and firstly we need to calculate overall thermal gradient, and we calculate 322.18 plus 286.04 and plus 306.47, and we got 914 and 69. Next, we move to thermal resistance. The formula is R equals to L over Ka. For brass, we got 0.52969. For stainless steel, we got 0.5935, and stainless copper we got 0.5539. So we got the thermal resistance. Next, we total the resistance, and we got 1.6743. For armate, the formula is R total minus 2R brass. So we got 0.6205. So thermal conductivity for middle section is 273 and 59.
As conclusion, we conducted a lab session on linear convection. We learned how to demonstrate how heat conducts linearly along a solid bar and around a solid disk of uniform dimension and materials. Farrell's law explained the behavior in both line and radial heat conduction. Increasing the area of the induction process boosted heat transfer, as evidenced by aluminum cylinders with varying radiuses. The inaccuracy from the lab station was noted for future improvement and safety precaution. So that's all for the lab 1 report. Thank you very much.